All right, hello, welcome everybody to the Connect Science series. Today we're very fortunate to have Frank Harrell coming to speak with us. So Dr. Harrell, Professor Harrell is a very prominent statistician that has been working on statistical methodology, including clinical trials research for several years. He is the founding chair of the biostatistics department at Vanderbilt. And he's also quite a prolific educator. I know I learn a lot from him through his blog and through Twitter. He has opinions on Twitter, and it's a very entertaining person to follow. He also has people that disagree with him that are also quite opinionated. So it's often a very entertaining learning experience. Today, he's going to share some of his knowledge related to the COVID pandemic in his area of expertise, which is the use of Bayesian statistics. One of his areas of expertise, the use of Bayesian statistics to improve how we learn and design, how we learn from and design clinical trials. Well, so I will be, oh, by the way, if you want to follow this, if you want to see this talk later or see the schedule for others, there's a link right there on the screen that you want to bookmark. That we've had a pretty awesome series during this work from home era, and you can see all the links there. All right. Well, the other thing I want to say is that if you have questions or comments, you should use the Q&A feature of Zoom. I will be monitoring that through the talk. I might interrupt Frank if I think it's necessary, or I'll wait till the end. He has predicted that he will finish with 10 minutes left before one to go through questions. All right, well, without further ado, Professor Harrell, take it away.
Raphael, I thank you for the nice introduction, and I really appreciate the Dana Farber Connect Science for inviting me to give this presentation. It's a great honor to be here, and I hope it generates some thinking and some controversy and some good questions. I'm sure it will, because I cover some controversial topics. And so in the time of an emergency, when you have a pandemic, it's actually an amazing opportunity to collaborate and accelerate collaborations and to do research and try to contribute to solving the problem of this dreaded disease. So it's kind of an accelerator, and at the same time, it brings out longstanding problems that we've had in clinical biostatistics for the last 30 years, because clinical biostatistics has been dominated by a fairly rigid, frequentist statistical mindset. And I think this is the perfect time for Bayes to be rising and to be used more than it has been. So we have a number of resources that we have created at Vanderbilt to get at this, and our work in the last couple of months has been sponsored by major new grants that we have from National Heart, Lung, and Blood Institute, which is really the part of NIH that's dealing with treatment studies for COVID-19, because it's mainly, not solely, but mainly a lung disease. And so this is a joint effort between Vanderbilt and Research Triangle Institute, North Carolina. So we have a big team put together, which is NHLBI Connects, and we have the Study Design and Analysis Core that's part of our Vanderbilt Institute for Clinical and Translational Research. And this webpage is, which is under hbiostat.org/PROJ for project/COVID-19 without the dash. This has a lot of resources in it, and the resources are sort of in two areas. One is the design, and one is the outcome variable and analysis. And so if you've seen COVID-19, you know it's a time of rising dominance of ordinal outcomes, which I've been waiting for decades, because there's a World Health Organization ordinal scale that's being used routinely as an outcome measure in COVID-19, especially for inpatient studies. And then there's a variety of other ordinal scales that extend that into more levels. And so we have this document, General COVID-19 Therapeutics Trial Design, that I'll be showing you well, actually, let's go to that right now. This is a very rich document. I think that's our latest one, and that's one that we'll be doing. I'll be going back to in a little while. I need to get back to where I was. Let's see. Sorry, 1 second. Figure out how to do the back button. So I'll be going through that document in more detail. And then we have another document, which is a few weeks older, which is our Bayesian fully sequential design and analysis plan. So this is the document that contains lots and lots of simulation of Bayesian operating characteristics. So when you're looking at sequential designs, you might want to know what's the mean time until stopping for efficacy, what's the mean time for stopping for inefficacy, or the mean time for stopping for a conclusion of similarity of two treatments. And so that's where you see a whole lot of simulations. We've captured a lot of discussions with some great statisticians nationally about statistical models for outcomes, especially related to ordinal outcomes and state transition models. And then there is a blog article that I'm going to show you about continuous learning from data. And then we have a discussion board related to Bayesian modeling, and a lot of general Bayesian material here with a lot of background information for using Bayes for designing treatment comparison studies. And then we have a new R package for Bayesian proportional odds model with random effects. And so we have a lot more tools now for hierarchical longitudinal ordinal models that will be very handy in COVID-19, and we're starting to use that. A lot more background with Bayesian model is related to components written in STAN by Ben Goodrich at Columbia, inner workings of STAN models, code repository, more discussion board. And then there's a lot of topics here related to my teaching materials, which has a link here. And I have several sections about ordinal outcomes in clinical trials and the proportional odds model, and how do you do Bayesian modeling, covariate adjustment in randomized trials, problems with p-values. There is a blog article showing how you use ordinal outcomes to get more power than with binary outcomes. And binary outcomes includes time to event outcomes, which are typically not very powerful. And a lot more blog articles about Bayesian methods and how I became a Bayesian. This is my second most viewed blog article. A litany of problems with p-values, and a lot of other stuff. So this page, which I should have put the URL, this hbiostat.org/proj/COVID-19, this has a lot of our resources. So I want to go next to this blog article, because this is really setting up for using Bayes sequential trials, continuous learning from data, no multiplicities from computing probabilities as often as desired. And so there's this quote by Edwards, Lindman, and Savage: "In a Bayesian analysis, it's entirely appropriate to collect data until a point has been proven or disproven, or until the data collector runs out of time, money, or patience." This is really fundamental. And if you think about this, this is how physics works. So in physics, they experiment till they have an answer, whereas in clinical biostatistics, we tend to calculate a sample size, and the way we calculate it is pure voodoo. And then when we get to the end and we find the sample size was very over optimistic because we powered the study to detect a miracle, and all we had was a clinically important treatment effect. And so you're left with nothing, and you end up stopping with an equivocal result. So in other fields like physics or using Bayesian methods, you don't really think the same way. And this is where I've had the most problem getting people on board, because they start to think about multiplicity, and they don't really realize there's two kinds of multiplicity. There's sampling multiplicity and there's parameter multiplicity. And when you're talking about sequential studies, that's sampling multiplicity. And so there's this fear that you're going to have a type 1 alpha probability that's going to be bigger than 0.05. And so this is just a story to try to show why that's not a relevant concept in sequential clinical trials. So I keep trying to come up with examples to convince people, and this is one that I've gotten some good reactions to. So you're imagine a totally different situation where you're working for the US military and you've got a new pattern recognition algorithm that determines whether a distant object is some sort of enemy weapon or enemy tank. And so you're in the field and you've got an image from a distant object, and this pattern recognition algorithm says the probability is 0.8 that that object is an enemy tank. And so the object now moves closer and the fog is clearing, and the probability is now 0.9. And so what is the relevance of the 0.8? Well, the 0.8 is replaced by more recent information, and now it's not as foggy. The tank is closer. So the 0.8 is utterly irrelevant, and the 0.9 is all that matters. We don't know, we don't care how we got there. Whereas the frequentist way of thinking would be this: of all the times that a tested object was not a tank, the probability of acquiring a tank-like image characteristic at some point grows with the number of images acquired. And it's just not surprising that if you acquire more photographs, more images of some object, a higher number of those images are going to look like a tank. So the frequency of the image acquisition, which in our clinical trial setting is the frequency of data looks, and the image sampling design, they alter the probability of finding a tank-like image. But that way of looking at the problem is really completely separate from the decision that you're trying to make. Is it a tank or not? Do we fire a missile at it? So the real-time decision is based on current cumulative data. An earlier tank look is of no interest once a later, clearer image has acquired. So a clearer image in our statistical parlance would be a higher sample size, more patients followed. And so analogously, with multiple data looks in a clinical trial where there's no treatment effect, the probability of having extreme data at some point, which would be a tank-like image, grows with the number of looks. That affects the type 1 probability, but not the true chance that the treatment works. So traditional statistics has multiplicity issues that arise from giving more than one chance for the data to be extreme. Whereas the decision we're trying to make is the decision, is it a tank? Is the drug efficacious? And that's really a different idea than looking at extremes in the data. So that's just one way to think about sequential testing and multiplicity. So if we look at how a trial might unfold, so let's say you have a trial that has a planned sample size of 1,000 patients, and you set an efficacy target, which is a Bayesian posterior probability of an odds ratio being beneficial, less than 1, is 0.95. So if we have a probability of efficacy that goes above 0.95, we're going to declare victory and act as if the treatment is effective. We don't have to make a conclusion that it is effective, but we're talking about actions here. So are we going to recommend the treatment for use with the public? So that's going to be our efficacy target. And we're going to not do the analysis until the 10th patient has been followed, the full follow-up. So this is our first look. So this is really, it's not the 100th look. This is really the 91st look is right here. So when you go from 10 patients out to 100 patients, you see that you have this evolution of the posterior probability. The posterior probability starts at 0.5 because the prior we used gave equal chance of harm as for benefit. Now, what happens as you follow your evidence for efficacy along this path where you get to your current look? This posterior probability of efficacy now, which is about 0.65, has just completely superseded everything that you knew before. And so there's no multiplicity because you just need to look at that one number. These are totally obsolete quantities. So they're just merely replaced. There's no multiplicity. So when you get to the 200th look, so we stopped over here before, now we have more unfolding data and our posterior probability is a little bit lower. But that, whatever that number is now, 0.63, has superseded what we had before. And all of these previous probabilities are obsolete. There's no multiplicity issue. Now let's suppose that you weren't going to have a formal DSMB meeting at the 231st patient, but the DSMB learns about a related study. We have an effort now to consolidate, to have a consolidated DSMB to help overview multiple related studies and have a unified DSMB report. Or they could have been a published study. And so let's say the DSMB sees this published study as relevant because it's a related treatment, and they decide to have an unscheduled meeting. Well, in the Bayesian world, you're just, we were at 200 before, now we're at 231. Anything to the left is obsolete. This posterior probability of efficacy at that moment of 231 has complete meaning, and there's nothing at all wrong with it. And so if you have an unscheduled meeting, there's nothing complex. It's all trivial in the Bayesian world. There's no alpha spending involved. It's just easy. So you're looking at current evidence, and that's all that really counts. At the 300th look, so our posterior probability has wandered around a little bit, but whatever it is there has superseded everything to the left. And then we get to the 400th look, and we have more wandering of this posterior probability. All we need to know right now is that one number. And then we get to the 500th look, and we have a posterior probability that's a little bit less than 0.9, say it's 0.85. So this study was designed for 1,000 patients maximum, but what if it had been designed for 500 patients maximum? Okay, what if the safety profile is looking fantastic? The current evidence for efficacy is a probability of efficacy, or in other words, the treatment's working in the right direction, is about 0.85. And it may be very logical to say, we don't have other treatments for COVID-19 that look quite as good as this one right now in terms of the effect size. And so we might say, we know we plan to stop now, but we're going to ask for more funding, and we're going to proceed by extending the study. So in the Bayesian world, there's no penalty whatsoever for extending the study. And you know that the Bayesian approach is honest, because you might spend the money and go to 600 patients and the posterior probability actually goes down. So you've wasted the money. So we have this kind of lemma in statistics that if something doesn't always benefit you, you know, it's not constantly biased in your favor, you get, it can hurt you, you get to use it when it benefits you. And so in the frequentist world, yes, go ahead.
Real quick, I'm curious what your thoughts are here on communicating to the public. So suppose you every week you give a press conference about your posterior. So one week you say it's 60%, the next week you say it's 85, the next week you say it's 55, the next week you say it, et cetera, right? Every week it's jumping around. How do you explain to the public that you know what you're doing and you're not just randomly throwing numbers out that are kind of all over the place?
Yeah, the vast majority of clinical trials, you're not going to be communicating this to the public, but you're going to place a burden on the DSMB. So DSMBs have to deal with a more complicated situation than they're used to, and they have to get used to seeing these kind of evidentiary measures. So this is really kept confidential for most applications.
Thanks.
So if you were a frequentist and you had the planned end of the study was 500, your alpha is already spent. And so if you look at the literature of sample size re-estimation, that's really what you might call unblinded sample size re-estimation. You'll see that if you extend the study, you have to discount the previously collected patients. So you might extend the study by adding 50 patients, but these 500 patients may be discounted as if they're 450 patients. So you pretend these are 450, you add 50, you're back with 500. So you've spent the money and time to add 50 patients, but it's not worth 50 patients because you have to be conservative because you have this alpha to worry about. So once alpha's spent, things get really messy and quite conservative. And in the Bayesian world, this just doesn't apply at all. So now we get to the 600th look. Now we're back to the case where the planned end was really 1,000 patients. And so the posterior probability is up there about 0.9. And then we see at the 660th look that we've gone a little bit above our target of 0.95. And so we are now hit our efficacy target, and that we pre-specified. So we might take an action of recommending this treatment be used. And so again, that last number supersedes all the earlier numbers. And these are just obsolete. They just no longer apply. They're out of date. So this number is totally okay. So when you go to, let's see, let me get to the right one now. Back in this continuous learning blog article, excuse me one second. There's a lot in here, and so there are simulations to back up what I was saying. And when you go down to this simulation part down here, you can see the R code, and it makes the whole thing very concrete. So one of the things you'll notice is when you're doing a Bayesian simulation, the programming is different than if you're doing a frequentist simulation. And it's quite enlightening to go through the program because what you're doing with a Bayesian simulation is you're simulating 50,000 different clinical trials. No two clinical trials might have the same efficacy. So you're not stuck on a null hypothesis. You're looking at the whole spectrum of positive, zero, and negative efficacy. And for each of these 50,000 trials, you're generating a true treatment effect like mu, and it could be from a prior, or you could generate mu just over a uniform grid. You can do it lots of different ways. Then you generate a clinical trial under that truth. So the goal of Bayes is to uncover the unknown truth, no matter what it is. So you don't think about hypotheses so much. You talk about uncovering the data generating mechanism. So the data generating mechanism comes from the efficacy of the drug, and it comes from patient-to-patient variability, which we can never do a whole lot about, except covariate adjustment helps. And we're trying to uncover the truth from the data generating mechanism, no matter what value of mu generated the data. And so we're going to do the analysis continuously. So we're going to do essentially infinitely many looks at the data, because we're going to look at the data after every subject completes follow-up, and we're going to stop at the instant that the posterior probability exceeds 0.95. Now, we're also going to stop for futility if the posterior probability of that is greater than 0.9. So this would be trivial efficacy or worse. So what happened with the 50,000 trials? 20,000 were stopped early for efficacy. 28,000 were stopped early for futility, 1,100 went to completion. And this is really the key element here. The average posterior probability of efficacy at the instant that you stop for efficacy. So the stopping was greater than 0.95, you have to overshoot just a little bit. So the average posterior probability at the moment of stopping was 0.961. Of all the trials that stopped early for efficacy, the proportion that were for which the treatment was truly effective was 0.96. So you see, these are just estimating the same quantity. That's just a little overshoot there, but these numbers are the same. So the point of this is this 0.961 is something that you might shout from the rooftop at the moment the study hit the target. And the fact that you looked hundreds of times is of absolutely no consequence in how well this number is calibrated. So the posterior probability is perfectly calibrated at every moment, whether you use that moment to stop the study or just continue the study. And so these are just the same thing. And you see the agreement too on the probability of futility. So this, if you go through these simulations and then you look also at calibration curve, just like we do for risk models, of the times the study was not stopped early, was the posterior probability at the 500th patient, was it well calibrated against the true probability of treatment effectiveness? And we see perfect calibration there in those 1,000 trials. So you can look at calibration like we do with risk models, and the posterior probabilities are perfectly calibrated. So let me, so we've gone through that sequential look there. And let me get back. When I go to this, this navigation, and then I go here to this design, I want to talk a little bit about this document, because this is our latest document, and I think it's very, very rich. General COVID-19 Therapeutics Trial Design. So what this has in it are common pitfalls in traditional designs, contrasting the Bayesian and frequentist statistical methods. So this is sort of the selling of the Bayesian method, and then the Bayesian design, and what sort of outcome measures are we going to have, and what sort of analysis are we going to recommend for longitudinal ordinal outcomes. And so this is a background section. This is the URL that has the overall navigation I've been showing you. And then the session, this is just to get people's attention about what is happening with clinical trials most often that we want to avoid. We can't afford this anymore, especially with COVID-19, but I think this applies perfectly well to oncology studies also. So one of our most common pitfalls is the absence of evidence is not evidence of absence problem, where somebody will do a study, the p-value is 0.3, and they'll conclude the treatment doesn't work, and the p-value has nothing to do with that. So Fisher was asked, what do you do when you get a p-value that's large? He says, get more data. That's all that it tells you. And so what happens very often is you get a p-value that's large, or larger than 0.05, for example, and you find out your power calculation was over-optimistic. You found out that you really can't conclude anything except the money was spent. And you might have missed a lot of opportunities to make the study more powerful by using an ordinal outcome instead of a binary outcome. But there's just a whole lot of things that go wrong. And then a key thing that is really taken for granted in clinical trials done by the traditional approach is that you should actually stop the study when you originally thought you should have stopped it. In other words, you're forgetting that the sample size calculation was pure voodoo, but you are operating within the constraints of the National Cancer Institute that wants to fund fixed budget studies. And so we have to get away from the fixed budget studies and start putting the money where treatments are looking promising, but we don't quite have the evidence yet, and we'd like to extend the study.
Can
So
I
that's where
Can I ask a question?
Yes.
This is coming from Jacob Rosenthal. There's always an element of subjectivity in the choice of prior. Even if you choose a non-informative prior, that choice will impact your entire analysis in some way compared to if you had chosen some other prior. How do you approach the choice of prior for clinical trials?
Yeah, and that's really covered in this document. And the short answer to that is it's an old argument that doesn't hold water anymore. And the reason is when you are deciding how to do multiplicity adjustments, especially if you have more than 2 treatments, where you have sequential testing, group sequential testing, and then at the end you have a p-value of 0.049, and you're trying to say, should we recommend this drug? Or if the p-value is 0.051, we're trying to translate evidence about data, which is what a p-value is. So p-value is the probability that somebody else's data will be more impressive than mine if my null hypothesis is true for them. So we're trying to take a probability about data and translate it to an action. You will never in your life as a statistician do anything more subjective than how do you translate a probability about data into a probability about treatment. So the prior distribution in Bayes is the least of your worries. But to help make people more comfortable, I really am a believer in using skeptical prior distributions because I would like to be able to convince a skeptic. So I don't really like flat priors at all for an efficacy assessment. And so if people agree on the amount of skepticism that you have in the prior before you launch the study and have any data, you really can solve this problem. Now, how much skepticism to use has to be settled upon by the investigators and possibly by FDA if this is FDA oversight for registration. But it definitely can be done. There's a lot of work going on at FDA and at pharmaceutical companies for how do you implement best practices for the selection of the prior. So the frequentist approach is far, far, far more subjective than the Bayesian approach. So I don't think Bayesians have to continue to apologize. And I have on that popular blog article about my journey to Bayesianism, I have a quote from John Tukey about better an approximate answer to the right question than an exact answer to a question, to a change in the question that you've made to fit what you're able to do. So the way I view Tukey's statement is the approximate answer is my prior may disagree with yours a little bit, but I'm trying to answer the right question. And that's our first goal. The first job as statisticians is to answer the right question. Does the drug work? And so that's what the posterior probability is trying to do. So that's something you can talk about for a long time, and there will always be controversy, but I think the Bayesians need to just stop apologizing. Now this goes in, we have this mind map now to help people understand the different paradigms. So we have this mind map for what the frequentist paradigm is doing in the situation where you're comparing treatments. So I would urge you to look at that, give me feedback. We have the mind map corresponding to that for how the Bayesian paradigm works. So just trying to make the paradigms clear to the non-statisticians, and I think it helps statisticians too. And then this is something new, which is a detailed table that compares frequentist and Bayesian side by side. And I think this is going to turn out to be pretty useful. And like with the mind map diagrams, I would appreciate getting feedback about these things. So look at this detailed paper, this detailed table. So it tries to cover a lot of bases and deal with sample size issues and multiplicity issues. And then there's the argument about the prior, and this gets into skepticism for the prior. And then this is something that is in that blog article I mentioned with the simulations. The Bayesian posterior mean is perfectly calibrated. So once everybody agrees on the amount of skepticism in the prior, at the moment that you stop, you calculate like an odds ratio and you get the posterior mean or median odds ratio, and you find that that is perfectly calibrated. So what your posterior median odds ratio versus the true efficacy that was generating your data set, that's on the line of identity, whereas the frequentist is going to overestimate the treatment effect if you stopped early for efficacy. And the fix for that is very, very complex, and I've never seen a clinical trial actually be brave enough to include that fix for bias of the ordinary odds ratio in a clinical trial publication. So then this just goes through more about sequential testing and sort of what I was showing you before. And then the most controversial thing is, what does type 1 probability protect against? And you'll hear people say, well, your procedure doesn't preserve alpha error. Well, it doesn't preserve alpha error because we're interested in maximizing the probability of making the correct decision. We're not at all interested in probabilities about data. And so this just goes into that in great detail, and it tries to argue the case that if you want to tie down a Bayesian procedure to be a hybrid Bayesian frequentist procedure, which a lot of people are still doing, you really have the worst of all possible worlds. You have a very hard to interpret result, and then you're not able to have efficient learning in a rapidly changing environment such as COVID-19. And so one of my more recent attempts at this is just looking at looking at diagnostic tests. And so the analogy would be to controlling alpha error would be, suppose a patient with certain symptoms underwent a series of medical tests and the patient's current probability of disease is 0.9, similar to our probability of efficacy. Someone computes for another patient, one known to not have the disease, the probability that at least one of the tests is positive is 0.2, similar to the type 1 probability alpha. The person cautions the physician that her diagnostic strategy has a 0.2 probability of at least one positive test, even if the patient is disease-free. And the smart physician will counter, you suppose that my patient is disease-free. That's the unknown that I'm trying to determine for my patient. The 0.9 that I computed is valid and does not need to account for the 0.2. So the alpha probability is a pre-study probability. It doesn't involve data in any way from your study. And it really, once you have data, the alpha probability is irrelevant. And we want to know probability about treatment efficacy. So this section, for those of you who are still believing that type 1 probability should be computed, even when you're using a Bayesian method, just know you're going to tie the hands of the Bayesian method. You're going to make worse the probability of making a right decision about treatment efficacy, and you're going to wreak havoc on the interpretation of the study. So that's what I'm hoping this section really gets at. There's a design section here, and this is more standard stuff. Then we get into the outcomes that I'm just going to cover briefly. So these are the different types of outcomes we have in clinical trials. So a binary outcome is your minimum efficiency outcome, and it assumes time of an event is not important. Time to a binary outcome or to the union of a number of binary outcomes in a composite outcome is going to be high efficiency if the event is very, very frequent. Like if everyone dies, you have a continuous measure, which is time until death. But if the censoring is high, a time to event and endpoint is not very efficient. A continuous response is going to give you very wonderful power. An ordinal response with at least 4 well-populated categories is going to give you very good power, much better than binary and usually better than time to event. If you have a longitudinal ordinal response that's measured daily or weekly, you can get very, very high efficiency if you have several well-populated categories, or if you have so many categories that there's only one patient in each category, because then you have a continuous variable, which is our best. A longitudinal continuous response has the highest power of any outcome that we know how to use in a clinical trial. So this just goes through more details and advantages of using ordinal outcomes. And what do we really seek in terms of outcomes? And see, I want to make, this is an example of a comprehensive ordinal outcome scale that could be used in COVID-19. And we're working on refining this right now. And there's some new papers that have just come out with some work around the world on defining a outcome scale that might have 20 or 30 levels to it that really take into account what matters to the patient. So uninfected might be your lowest outcome. Then you have some virus detected, but the patient's asymptomatic. You get into symptomatic. You symptomatic, but you have some complications like deep vein thrombosis. You have to be in the hospital, but you don't need oxygen therapy. Now you need oxygen therapy. Here you need invasive oxygen therapy. You might have a really bad clinical outcome all the way up to pulmonary embolism or need for renal dialysis or stroke or death. So death is generally our worst level of outcome. So when you use an ordinal outcome, you can see that you can get a benefit-risk trade-off built into your primary efficacy analysis. You're breaking the ties in the outcome, and that's what gives you statistical power, and it gives you a lot more clinical relevance. And so this is really something that we're pursuing quite with a lot of vigor. And if you think about an ordinal outcome, a lot of the things we do in clinical trials are really special cases of this. So if you're looking at a recurrent event analysis, so you have multiple recurrences of cancer or you have multiple hospitalizations, that's really a special case of a repeated ordinal outcome. It could be a repeated binary outcome with a longitudinal random effects logistic model. So that handles recurrent events really well, but the events could be of different severities. So if you have hospitalization, that might be a recurrent event that's y is equal to 1, but y is equal to 2 might be death. So you'll count death as worse than hospitalization. If you had death as your only outcome and you have a repeated ordinal outcome, that the odds ratio from the proportional odds model is the hazard ratio in an ordinary Cox model for time to an event, if your interval risks are fairly small. So this approach, in the special case of only 2 categories here, where one of those is death, it reduces to the Cox proportional hazards model. So that's another advantage of this particular approach. So we see in cancer studies, say, time until a tumor gets bigger or the patient dies. Well, you can distinguish those 2 events and count death as worse with a repeated ordinal outcome, and you'll have something that's more clinically relevant and have higher power. So this goes through the relationship to time to event studies, and then what are the issues with analysis. And so we've developed a new R package that's called RMSB, which is on CRAN, and this is really using STAN and R-STAN Bayesian modeling capabilities to do random effects, proportional odds, ordinal logistic model. And we have also implemented the partial proportional odds model when the proportional odds assumption is not satisfied. And we've also developed in this package general censoring. So this really comes into play when you look at your outcome variable. And if there's certain things that are not assessed, let's say you know somebody's doing great and you know that they're not dead, but let's say in a given week, you don't assess all of these things. Well, that would be interval censored. So the patient might be interval censored between 3 and, let's say, 3 and 15. So you would just treat the ordinal outcome on that day or that week as interval censored. And now you have a really general way to handle a different density of information over time throughout the follow-up. And this Bayesian modeling package handles that, and I think a very nice way. So this goes through a lot of details about longitudinal outcome, and then what happens if you want to relax the proportional odds assumption. So this is going to be a treatment effect, and we're adjusting for age and SOFA score, which is kind of an organ dysfunction score. And this is the Bayesian logistic regression model. And then we have a second formula here, which is just treatment. So this is the departure from proportional odds is going to be just for treatment. And we're going to have the departure coded this way. The treatment might affect mortality differently than the way it affects the non-fatal outcomes. And so I think this is a very powerful way to think about it because the clinicians are very interested in knowing, since the ordinal scale is going to get more of its information from the non-fatal outcomes, which are more commonly occurring, what sort of evidence we have that the treatment is moving death in a similar way that it's moving the non-fatal outcomes. So this notation says constrained partial proportional odds model, where we have a special effect of just this variable treatment on death, and you can actually get out of this analysis the posterior probability that the odds ratio for treatment for death is different than the odds ratio for treatment on the non-fatal outcomes. And then you can look at this longitudinally, and then you can translate a longitudinal model into all the other kinds of estimates we're used to getting, like expected time in state. And there's a lot more. And then covert adjustment, we should be doing that in every clinical trial we ever do. I think it's really an ethical issue if you do not covert adjust, because that means you've inflated your sample size by not explaining easily explainable outcome heterogeneity. So you really never want to make the mistake in statistics of explaining heterogeneity that's easy to explain, such as by adjusting for age or extent of disease at baseline. So that will lower your sample size, and that will give you a more tailored treatment effect, and it gives you the basis for looking at heterogeneity of treatment effect.
So someone has a question about this. These outcomes do not all seem ordinal to me. This comes from Sam McDonald. These diagnoses clinically have a wide variety of severity. I feel like this would affect the analysis using this outcome variable, would it not? How do you handle varying disease severity within each category?
So these are a first attempt to capture varying disease severity in terms of what matters to the patient, and also giving weight to invasive things, because that's there's a resource usage issue with the ICUs being short of ventilators. And so, but there are the two new papers I mentioned that I just got yesterday from a worldwide collaboration where they surveyed 9,000 patients worldwide and gave them about 30 different endpoints. Many of them are here. And they came up with some recommendations for that are based on patients' opinions about how you should rank order things. So we'll be looking at those papers very carefully. They just came out like yesterday. But we also are probably going to launch a more restricted clinical consensus process, because this is really a statistician's view on these things. These are things, this is an ordering I made up. The expert clinicians are going to want to re-rank these things in terms of clinical importance. And the question is a key question. And this is just a very rough draft.
Thank you.
The main thing you want to use to guide your thinking is you want to break ties, because ties are the enemy of statistical power. So it's a great question. So a lot more stuff here, and you'll see sprinkled along the way in this document links to resources and a lot more about covariate adjustment. How do you report the results when you're doing a longitudinal ordinal? So this goes into how you might report the results in terms of probabilities of various outcomes as you go up the hierarchy of the ordinal outcome. And more about reporting results when you have longitudinal. So by having a longitudinal ordinal variable, just like you can have a time-dependent covariate in a Cox model, you can have a treatment by time interaction. And so you can estimate the time-varying treatment effect. And I have a web page that I link to here where I show how you can get exactly a Cox time-dependent covariate analysis using longitudinal binary logistic model. So by estimating the time-dependent treatment effect naturally from this longitudinal model, you can really provide a lot more information. So there's a lot more stuff here about interpreting and looking at consistency with mortality. How do you display results? There's some comparison to state transition models and some key references that I would recommend you to. And I just wanted to see if there was anything I wanted to bring up in closing that I didn't get to. I think the going to this page is going to give you links to a lot of useful material. And I think I'll stop there and leave time for discussion. I really want to thank everybody for putting up with me.
Thank you. That was great. So I want to point people to the chat if they want to see some of the links for Frank's material. I also include his Twitter handle, so those that want to follow him. So there's one question that I decided to leave for the end because it might be more open-ended, from Lorenzo Tripa. He's asking, do you know if FDA is open to approval decisions based on fully Bayes analyses?
And I have to mention a disclosure. So I work for the FDA for the last 4 years, 25% of my time in the Office of Biostatistics as an expert statistical advisor. So my main job at FDA for the last 4 years has been to foster the use of Bayesian methods, and been on many working groups. And these working groups, my time at the FDA ends this month. These working groups are going to go on, but there is a really new atmosphere at FDA, and they're getting a lot of submissions from pharmaceutical companies. and needing to gear up to be able to evaluate those and work with the companies and figure out how to specify priors and all that. So what has happened is the FDA is actually a lot more open than people think they are. And some pharmaceutical companies are stuck in the past and are kind of afraid to use this. Some of them are really ahead of the game and are doing brilliant work with Bayesian design. What I'm working with now, I haven't really worked with National Cancer Institute, but I work a lot with National Heart, Lung, and Blood Institute. I think NIH in general has been further behind the curve than pharmaceutical companies in using Bayes, and we really need to work on that and get NIH to be very comfortable. So we're actually producing a series of videos explaining these concepts, many that I talked about today, that I think are starting to help already, and we're hoping to keep getting better at these videos to help, especially non-statisticians. But FDA is getting a lot more open to this, but they do want it to be well thought out. And there are guidance documents that are being drafted right now that will help people know what FDA is expecting.
Thank you. So somebody asked if you can show the link to the R example early in the lecture.
Yeah, I'm going to bring that up.
All right.
So if you go to hbiostat.org/R, you get to a whole lot of R stuff with different packages, including our clinical trial reporting package, H report. But this one is really the RMSB, so it's Regression Modeling Strategies Bayesian. And if you go to this one, that's that link. And this is a very, very extensive document that has a lot of examples in it that I think are interesting, because it also compares longitudinal models to state transition models and lots of other stuff. And so this goes through proportional odds, binary logistic, partial proportional odds to relax the proportional odds assumption, how to deal with random effects with longitudinal data, how to deal with sensor data, like you might have some elements of the scalar not collected on certain days. How do you do multiple imputation with Bayes? How do you select priors? And so this just has a whole lot of goodies in it. And when you look at the code, you'll see code for all the examples, and you'll see output. And one of the things, like here's a Bayesian Wilcoxon test output here. One of the things that I am most think is kind of cool is at some point in here, there is an algebra for getting posterior probabilities to make it really, really easy. And right now I'm forgetting where this is in the handout. You see a whole lot of posterior probability distributions here, how to get contrasts with Bayes, general contrasts. There's just, so this says, give me a function that calculates posterior probabilities from the model that I just fit. And then I can say stuff like, what's the probability that beta 3 is positive and beta 1 is greater than 1.5? So that probability is 0.133. What's the probability that the absolute value of beta 3 is less than 0.25? That's this. So you can see how natural it is to get the evidentiary measures you need from Bayes once you fit a model.
So great, thanks. So I have a question. So you probably know this about me, that I don't consider myself frequentist or Bayesian, but rather practical. And as a data analyst, I basically see all this as just a bunch of toolboxes that I could pick from. And I use the Bayesian toolbox often, and sometimes I don't, because it's, it introduces too much flexibility. And that's what I worry a little bit about in the case of something like the FDA, where it's not about the philosophy really. It's about having more flexibility. So if you have a very constrained process, I know it has its limitations, but one of its advantages is that you can't manipulate it. It's hard to manipulate them, at least if you are honest. So I'm worried, I'm wondering what you think about the fact that if a pharmaceutical really wants something to come out positive, that they'll manipulate the flexibility of the Bayesian approach in a way that does it.
So that's one of the easier questions you could give me. So you're setting something up without knowing it, Raphael. But it's been said that any company that wants to cheat with a prior distribution would be the easiest company to catch you would ever find. They would be stupid to do it. It's so easy to uncover that trickery. But the bigger point is Bayes is much more pre-specified than frequentist, and this is not appreciated well enough. So why do I say that? Well, with Bayes, you're pre-specifying the prior, so you're pre-specifying how you're going to interpret the final result. You see subjectivity in the frequentist approach. So there are senior medical...
So I'm sorry, let me interrupt you. You're saying that this has to be pre-specified even before, you would require this specification to happen before any data is observed?
Of the prior, yeah.
Okay, that
and
helps.
In the model. And so what happens at FDA, there are senior medical reviewers that say, I'll know the evidence when I see it.
Okay.
And this is really causing problems because they will start to say, well, the p-value is 0.051, but this other study looked good, so we'll give them the benefit of the doubt. Or it's 0.049, I don't like it because they really had a multiplicity and they didn't admit it. There's another study where the p-value is 0.2, so I don't like the 0.049. You see subjectivity coming in every day.
Yeah.
So Bayes actually is way more pre-specified than frequentist.
Okay. I mean, can be.
It can, if you do it right. If you do it right, yes.
So second question is, one of the things that my generation really admires you for is the fact that you were very early as a chair, you were pushing for the use of R. And it was a great thing to see from the outside because my generation, we were all using R, but it was hard for us to convince sometimes the previous one. So that wasn't a question. I was just thanking you for that. But the question, the question that I have is, do you worry about the fact that we're still using SAS for a lot of things? Like I worry about the cost in particular.
Well, the cost
and perhaps
is
even reproducibility too. But yeah, so like what if they jack up the prices? There's certain things that are so hardwired right now that I don't know what would happen. Like, can you see a future where we translate all these SAS programs into R or Python?
Yeah, and you know, some major pharmaceutical companies are completely abandoning SAS. They can't afford Pfizer. 15 years ago, Pfizer was paying $10 million a year in SAS licenses. Wow. And so SAS is actually a disaster for us, and it is holding people back because it's not only not implementing the most modern statistical methods, it's costly, and we're having to hire more programmers because SAS programming language, especially the macro language, is 20 years out of date. So it's the worst of all possible worlds to be using SAS in this day and age. And what pharmaceutical companies are going to find is the number of SAS macro programmers that they no longer need, which is where they're really spending money, is going to be frightening. And so once you move into R, so I dropped SAS overnight. After I'd used SAS for 23 years, I was the first SAS user, in fact. And,
first ever? Wow.
and the first SAS user outside of the SAS group in North Carolina. And so I dropped it overnight after I visited Mayo Clinic and saw Terry Thurno using the S language in 1991. And my productivity shot up dramatically, even within a month, over what I was doing with SAS.
So I understand that, but think about, like, yeah, I'm with you 100%, but there's all this inertia and there's all this code already in place that would have to be rewritten. That's what I don't know if you've accomplished that. Maybe your department doesn't run as big clinical trials as we do, but now we have a lot of legacy code in our groups that it's really my main concern if we're going to completely switch over.
There are companies that sell legacy code translators to R.
Oh, is that right? Okay, maybe I'll contact you about that.
You have to, I don't know any of them, but you might look into that. But I will say, this is my final verdict on this subject, which is a very touchy subject. if I read a paper in the medical literature and I read what statistical software they're used, and if it was SAS or SPSS, I make a prediction that things will turn out to be linear. And lo and behold, in the analysis, things were linear. And why is that? It's because SAS and SPSS make it difficult to not use the defaults. And by default, they want things to be linear. And so covert effects are almost never linear, but for some reason, SAS and SPSS users find linear effects. That's a statement about how the software is actually holding them back.
All right. Well, thanks again for a great talk and a great discussion, and providing all these links. I can see a lot of interest. We have all the links on the chat, so take them now, because as soon as we leave, I think this goes away. But yeah, anyways, thanks again, Frank, and good luck with everything.
And thanks, Raphael, and thanks for getting me the opportunity to convey the deep philosophical thought that every person is entitled to my own opinion.
All right. Thanks again. Bye-bye, everybody. Thanks for joining.